So that's our goal today. Our goal today is take a function and graph its derivative. And so we're going to start off really easily with this, where we're going to take a look at a function that we know the equation of, and then we're going to graph its derivative from that, which should be easy because we could just take the derivative and then graph that equation. But then we're going to move into where we hopefully will be able to graph these derivatives without having to know what the equation of the original function is. So we're going to start with a nice easy one, x squared minus 2x plus 1. So that's the function I've drawn here. And we're going to graph its derivative. So first off, what's the derivative?
2x minus 2.
2x minus 2, right? It should be a linear equation, right? Should have a y-intercept of -2, and it should have a slope of 2. So I'll just plot a few of those points there. And surprisingly, I actually drew a line that sort of went through the points. There's our derivative. Good? Easy enough?
Yeah.
All right, cool. That should have been easy. So do you notice anything about a relationship between the derivative and the original function? If not, that's okay, because we've only just done this one, and who knows. Yeah. But do you notice anything? Anybody notice anything that they find interesting?
It intersects at the vertex.
All right, this one intersects at the vertex. This is true. Okay, that's a good thing to notice. Anything else?
It's tangent to the original function.
Sorry, say that again.
It's tangent to the original function.
What do you mean by it's tangent to it?
It's like pretty much perpendicular to the certain point of the function.
Okay, so like where it crosses through over here, you mean? That it's perpendicular to the function there?
Yeah.
Yeah, okay. We'd have to do some calculus there to figure out if it was exactly perpendicular, but it definitely looks like it could be, right? And it happens to, we'll note it happens to cross through a couple of times. It crosses through twice. Anything else you guys notice? All right, that's fine. That's good enough for now. We'll probably start noticing more stuff as we go through. All right, so here is a new function, x cubed minus 3x. X cubed minus 3x, and we want to graph the derivative. So we should probably figure out what the equation of the derivative is. So what's the derivative of x cubed minus 3x?
Three x squared minus 3.
3x squared minus 3. And let's see, that's got a y-intercept of -3, right? So I'll put that in there. And then it's just a parabola after that, right? It's a fairly steep parabola. If I plugged in 1 for x, I'd be at 0. If I plugged in -1 for x, I'd be at 0. And then if I plugged in 2, I'd be already up at 9, right? I'd be, this is getting very steep very quickly, right? I know it doesn't, my parabola doesn't look spectacular, and that's just because I'm trying to draw on this laptop screen here. But all right, anything we notice about the relationship between this function and its derivative graphically? Assuming that was a nice looking parabola there.
They're both unbounded.
Okay, they're both unbounded, so so the derivative increases without bound as it goes towards infinity and negative infinity, whereas the original function increases without bound as it goes towards infinity, right? And decreases without bound as it goes to negative infinity. Okay. but either increasing or decreasing without bound on both of the endpoints, okay? Or both of the ends. Good. Anything else? Nothing else? Okay, that's fine. If you don't see anything else, that's fine. Let's do another one. All right, so here we have the function x to the fourth minus 5x squared plus 4. I've already got it nicely drawn here for us. And what's the derivative of this?
4x cubed minus 10x.
4x cubed minus 10x. Okay. And then to figure out how to graph that, it probably is good to figure out x-intercepts first. So 2x, and that gives us x squared minus 5, right? Which means that this derivative should have an x-intercept at 0. And it should have an x-intercept at plus or minus the square root of, oh, sorry, that's not x squared, that's 2x squared. Plus or minus the square root of 5/2, which is the square root of 2.5, which is, I don't know, somewhere between 1 and 2. Somewhere here-ish, it's going to have x-intercepts. And let's see, I'm not going to go through and try and make this, you know, completely perfect here, but if I were, let's say, to just try to graph a normal looking cubic that sort of looked like this, what would a cubic that started with 4x cubed look like generally? Sort of increasing and then decreasing and then increasing again, probably. Do you guys agree with that? That's what a cubic that has a positive a value looks like. Something like that. All right, anything we notice here? Any relationships between this function and its derivative?
At each time that the derivative crosses the x-axis, it's like splitting the difference between the two closest of the original function.
The two closest? What do you mean?
So if we just take the origin one, it's splitting the difference between. It could just be a coincidence, but it happened in the last one also.
All right, so we note that this x-intercept is sort of splitting the difference between these two x-intercepts of the original function. And the same here, this x-intercept looks like it's splitting the difference between those two x-intercepts. And you mentioned up here, it looks like it was doing the same thing, right? This x-intercept was splitting the difference between these two, and this x-intercept was splitting the difference between these two. Well, and this one, well, this x-intercept was the same. There weren't two to split the difference between, but it did hit that exact same one, didn't it?
Yeah.
Hitting the same point is sort of like splitting the difference between a point and itself, I would say. So that seems like that's held up for all three of the ones we've done. Let's take that idea just a step further. And what else do we notice at each of these x-intercepts about our original function? Not just that it's splitting the difference between these other x-intercepts on it, but what's happening with our original function at this x-intercept?
It's at a peak.
It's got this peak right here, right? It's going from increasing to decreasing. It's got a local maximum. And what about this one?
It's got a minimum, or it's switching from maximum.
Yeah, and same thing here, right? And if we go back to the last one we did, well, let's see it. This x-intercept, when our derivative is 0, what's happening to our original function? It's going to have this local maximum, or it's going to have this local minimum. And same thing here, right? If we have an x-intercept on our derivative, a place where the derivative is 0, we have this local minimum. And that's something we've talked about previously, but we maybe didn't think about it graphically, right? That when we graph the derivative, it should have an x-intercept wherever our original function has a local minimum or a local maximum. We feel okay about that? That will almost always happen, and it will always happen if we have a nice smooth curve for our original function. Anything else you notice that's in common between all three of these that we've done?
Oh wait, what was the last thing you said? What happened again?
The last thing that I said, what?
Happened with
Just
derivative.
that the x-intercepts of our derivative were local maximums or local minimums of our original function. I'm going to have all these things that we're discovering. I'll have them all written down eventually on a slide. So
All right.
don't sweat about writing them all right this second.
I think when the original function has a x-intercept, the derivative has a minimum or maximum too.
When the original function has an x-intercept, the derivative has a maximum or a minimum. Okay, so let's think about that. Let's just look at this one then. The original function has an x-intercept, but does our derivative here have a maximum or a minimum?
No, but that's because it's the line.
No. What about this one? Okay, so our on this one, when our derivative had an x-intercept, sorry, when our original function had an x-intercept, that's what you were saying, right? So
Yes.
Here's a place where our original function has an x-intercept, and this one does have a local minimum there, doesn't it? True?
Sure.
Yeah. But at this point where it has a x-intercept, it does not have a local min or a max. Same with this point. So I don't think we can say that that's true no matter what, but it does. There is a reason why at this particular x-intercept, we do have a local minimum here. What else is happening with this function at this point? Not just that it's crossing through the x-axis, but what else is going on with it?
It's decreasing.
It is decreasing there. That's true. Let's think about what if I just drew the piece of it up until I got here? It would look like this, right? Until I got to that point where my derivative had this. So to x equals 0 is where the derivative has the local minimum. What can you say about this? How could you describe this? This little
Parabola.
Okay, it looks like a parabola, right? Part of a parabola, at least. How could you better describe this parabola? How could you define this parabola a little bit? Not with an equation, or what do you know about it?
Arc.
I mean, it is just an arc, but what about it? What about its shape? Or what could you tell me? What's one specific thing you could tell me if this was a parabola? What could you tell me about its equation? Let's say.
It's negative.
Meaning that the a value would be less than 1, right? Is that what you're saying?
Less than 0, but yeah.
Yeah, why did I say less than 1? That's weird. I don't know why I said that. I know how positive and negative numbers work, don't worry. A value is negative. Why did I say less than 1? That's really weird. Yeah, a is less than 0. All right, now what about over here, this other piece of it, where it looks like, I'll just draw it over here, where it looks like this. Also looks like a parabola, right? What could you tell me about that parabola's equation?
A is greater than 0.
A is greater than 0, right? And there's a specific word we use to define both of these situations where A is less than 0 for a parabola or where A is greater than 0 for a parabola. What do we use to define that? Do you know? Anybody know?
Wait, what is A supposed to be again?
A is the leading coefficient of a parabola. So we're looking at this particular piece of this function right here as if it was just one piece of a parabola, and then we're looking at this piece as if it was one piece of a parabola also. Feel like maybe you guys were never taught this. This is a parabola that is concave down, and this is a parabola that is concave up. Have you heard that term before, those terms?
No.
No. Oh my gosh. What do they teach you all? I always worry about all these previous classes. I don't know what they teach in those. Concave down means that it looks like this. Concave up means that it looks like this. Right? A downward facing parabola is concave down, and upward facing parabola is concave up. Okay? And this whole idea of concavity is exceptionally important. And we're going to deal a lot with concavity. So we might note that where our derivative had a local minimum, our original function changed from being concave down to being concave up. Does everybody see that at this x value, at x equals 0, right here at the y-axis, where my derivative had a local min, my function went from being concave down to being concave up. Everybody agree with that, or no?
Yes.
Okay, let's go back to this one. Did my original derivative that I found, just this line, does it have any local maximums or local minimums?
No.
No. And is there any time in here where the concavity changes from being concave up to concave down on my parabola?
No.
It never changes, right? It's always concave up, isn't it? Do you guys agree that this parabola is concave up?
Yes.
Yeah. And no changes in it and no local max or min. And then right here, well, let's see. There's definitely a local maximum here-ish and a local minimum here-ish. And what does it look like going on between there? Well, I'm going from concave up, and then right around here where I have this local maximum on my derivative, my original function turns to becoming concave down. And somewhere down here where I have this place where my derivative has another local minimum, I'm changing from being concave down to being concave up again. So anywhere where my derivative has a local max or a local min is telling me that my function, my original function, is changing from being concave up to concave down. I said those backwards, but concave down to concave up, or vice versa. So this particular one, we started concave up, we switched to concave down, then we switched back to concave up. Everybody see that or no?
Yeah.
All right, cool. That's 2 of the 3 things I wanted us to notice. Anybody notice one more thing? Tell me about my derivative there where I circled it. What can you tell me about my derivative there?
As x approaches infinity, as x approaches negative infinity, y approaches negative infinity.
Okay, true. What else? That is definitely true. just tell me even more basic than that. Don't try to get too technical. What can you tell me about the values of my derivative?
They're negative.
They're all negative, right? We're going to say derivative is negative here. Well, if the derivative is negative, what's happening with my function everywhere where the derivative is negative? How is it behaving?
It's decreasing.
It's decreasing. Derivative is negative, the function appears to be decreasing. And when my derivative is positive, what does my function appear to be doing?
Increasing.
Sure does look like it, right? Let's look here. Let's see. My derivative was positive here. And what's my function doing on that interval?
Increasing.
Increasing. And in between here, this little section here, my derivative is negative. And what's the function doing? Looks like it's decreasing, right? And then my derivative is positive again. And what's my function doing again? It starts increasing. Same thing here. When my derivative is negative, right? My function is decreasing. As soon as my derivative becomes positive, all this place where it's positive, my function increases. And then when my derivative is negative again, the function decreases. And then when my derivative is positive again, the function increases. Everybody see that? Or no?
Yeah.
Yeah.
All right, cool. Those are the things I wanted us to notice. So here's what we've noted. Our minimums or maximums on our graphs of f, our x-intercepts on the graphs of f prime. We noted that any place where our original function changes concavity, we had a local minimum or maximum on the graph of our derivative. And we noted that anywhere where our function is increasing, the derivative was positive, and anywhere where our function was decreasing, the derivative was negative. And then we didn't note number 5 yet, but we will now note that at any point on our graph that has a cusp, a corner, or a discontinuity or vertical tangent line will give us a discontinuity on the graph of our derivative, which we didn't have any of those because we were just dealing with nice polynomials, but we will want to note that. I'll give you guys a second to write that down. Do those all make sense? Do we kind of see all that from the nice little graphs that we drew?
Yeah.
Okay, cool. So what we're going to try and do once you guys write that down is we're going to just try and take some functions where we don't actually have the equations and see if we can draw a sketch of what the derivative should look like. That's our goal. So I'll give you another 30 seconds or so, a minute to write all that down, and then we'll move on. Anybody have any questions on that, or everybody okay? Everybody got that down? All right. Everybody good or no?
Yes.
All right. Cool. So we're going to start with a very easy one. I'm going to start with just a nice little linear looking equation here. And what should we already know about this equation?
It has no local minimum or maximum,
Okay. No local minimum, no local maximum. Definitely true, which
and the slope is
means
consistent, meaning the
always-
derivative is constant.
right, our derivative is a constant, right? Because the slope of this is always the same. In fact, what is the slope of this always?
2x.
Slope is not 2x, slope is 2, right? The
Oh,
equation of this, 2x minus 3, so its slope is always 2. So if the slope or the derivative is always 2, then this should just be green. This should always just have a derivative that is a flat horizontal line, or at least as flat of a horizontal line as I can successfully draw, at y equals 2. Right? And it should follow the only criteria that's met here, that since our function is always increasing, our derivative should always be positive, and it is. Right? Good or no?
Good.
All right. So now we'll make it slightly more difficult. Here we have a nice little parabola, or at least it looks like a parabola, generally shaped like a parabola. Our parabola has a local minimum, right? At x equals 3. And so what should happen with our derivative at x equals 3?
There should be an x-intercept.
Exactly. So we'll plot that x-intercept there. And then what's happening to the left of x equals 3 with our function? It is doing what?
decreasing.
Decreasing, which means that our derivative on that entire interval should be
Decreasing.
not
It should be
necessarily
negative.
decreasing, it
Negative.
should be negative. Right? And then after x equals 3, our function is increasing, which means our derivative should be
Positive.
positive, which means that we should have this nice linear looking derivative for our parabola
Yeah.
that crosses through and is negative when our function is decreasing and is positive when our function is increasing. Now, the slope of this is sort of important, but we don't need to be like completely 100% perfect and exact with how steep this is. We want to have a sketch that is generally pretty correct. So what I would normally do is I would take a point or two. I'll say, all right, let me look here at x equals positive 1. If I were to draw the tangent line to this function here, try and do that again. It's got a fairly steep slope, maybe -6, -7, something like that. Would you guys agree that that's got a fairly steep negative slope?
Yes.
Yeah, maybe -6 or -7. So somewhere down here where I'm at x equals 1, I should be at a value of, -6 or -7. And then I just sort of connect it and make it look pretty good. Does that make sense? If you happen to draw yours and it looked more like, oh, that wasn't very good, and it happened to look more like this, that'd be fine. If you happen to make yours a little bit steeper like that, that'd be fine. It's just a sketch. It's just a general idea of what it looks like. Good or no?
Good.
All right. Let's try to do another one. Thoughts on this one?
X-intercepts at the minimum and maximum.
All right, so we have a minimum here, looks like at -4, so we'll have an x-intercept. And a maximum here at x equals 2, looks like, so we'll have an x-intercept. All right. Now, what does our original function basically look like? Looks like a
X cubed polynomial, which is negative.
right. Looks like a negative x cubed type polynomial, right? Which means that
Negative x squared derivative.
our derivative should look something like a parabola that is facing down. So we've got, let's see, our function is concave up here till about maybe x equals -1. And then it switches to being concave down, which tells us that we need to have a local minimum or a local maximum on our derivative. Okay. And we should be able to determine which one of those it is in multiple different ways. One, we said this needs to be a parabola that faces down, that's concave down. So it should be a maximum somewhere up here. But also, we should know that our original function is doing what here in between these two points, between x equals 2 and x equals -4, our function is increasing, which tells us that the derivative on that entire interval needs to be positive. Up here. So if we look sort of right here in the middle where that change takes place, what would you say the slope of the function right at this point is? Maybe, what do you think?
Like 3 or 4.
3 or 4? All right, sure. I'll just plot 4. That seems good to me. And then we're going to have a parabola that's just facing down. And is this perfect? No, but it's a general sketch of what it should look like. And if we try to check all of our different criteria, well, from -infinity to -4, our function decreases, which means the derivative should be negative, and it is. And then in between -4 and 2, when our function increases, our derivative should be positive, and it is. And then to
Wait,
the
you
right
mean
of
2 to 4?
What?
And then -2 and then 4?
From -4 to 2.
Oh, I thought you were talking about the y value. Okay, never mind.
No, I'm only talking about x values. Yep. So from x equals -4 to x equals 2, our function increases, right? So our derivative is positive. And then from x equals 2 to infinity, our function decreases, so our derivative should be negative. And then at our local min and local max, we had x-intercepts. At the place where it changed concavity, we had a local maximum on our derivative. Good or no?
Good.
Awesome. All right. Oh, there's a fun one. Kind of looks like, I don't know, some sort of weird absolute value function. Yeah. What can you tell me is happening at x equals 2 on our original function? What do we have?
X equals 2 or x equals -2?
Oh, sorry, x equals -2. Did I say 2? Sorry. Okay, I'm having trouble with positive and negative today. I don't know. That's a problem.
Right before it reaches its very bottom, the derivative is just a constant negative, but then it jumps right to a constant positive.
Right. Our original function has a corner there. Right. I've got a linear piece to the left and I've got a linear piece to the right. And so the slope of this linear piece is -1. So my derivative should just be -1 all the way up until I get to x equals -2. And then as soon as I hit x equals -2, because I have a corner, that was our fifth little thing that we were noting before, I should have a discontinuity on my derivative. So I've got an open circle. Then our slope becomes 2, right? Up 2 over 1, up 2 over 1, up 2 over 1, another linear piece. So we have now just immediate jump to x equals 2. And that's what our derivative for this should look like. Good or no? Any questions?
Why are both open circles?
Because there's no derivative at this specific point, because from the left, the derivative is -1, and from the right, the derivative is 2. And so since derivatives are limits, the limit or the derivative from the left and the limit or the derivative from the right have to be equal to each other for it to exist at that point. And since they're not equal to each other, that derivative does not exist at all at that point. Does that make sense?
Yeah.
Any other questions on that one?
Is the discontinuity always a jump?
Generally so. Let me think about that for a second. If you have a corner, yes. If you have a cusp, also yes. If you have a vertical tangent line, not necessarily. And if you have a discontinuity on the original graph, also not necessarily. So if it's a corner or a cusp, yes, it will always be a jump discontinuity. But if it's a vertical tangent line, or if it's a, I think about that, vertical tangent line. Yeah, if it's a vertical tangent line or if it's a discontinuity on the original graph, then not necessarily. But a corner or cusp, always a jump discontinuity.
Okay, so would you have to, or would it be okay to just kind of guess which discontinuity is for vertical tangent line and regular discontinuity?
Well, I mean, you'll just want to look at what's happening on either side of that discontinuity. So like generally, yeah, probably it will be a jump discontinuity if the original function has a regular discontinuity. But it could be something like, perhaps I draw my original function like this. Well, that was, the slope still stays the same, but I just have a removable discontinuity on my original function. And so if I, this way the slope is, -1, and then it's still -1. So my derivative would look like -1 all the way to that point, and then still -1 afterwards. But since I don't exist at that point, I have to have a discontinuity in my graph. So rather than being a jump discontinuity in that case, it would be a removable discontinuity.
Oh, okay. So it just depends on what the graph's doing.
Exactly. Yeah. So if I had a removable discontinuity and it was doing this instead, well, then I'd have to jump up here and look like this, and then it would still be a jump discontinuity. It just depends.
Okay, got it. Thank you.
Yep. I wouldn't be too stressed out about that though. Like it's not going to happen very often that they give you something like that, most likely. Usually there's like one question where they ask you to graph a derivative in the multiple choice. So like it's usually a pretty straightforward one. We try to do some weird cases just in case, because every once in a while they do. Like this one, nice weird looking case like this. So you guys want to see if you could do this one on your own?
Yeah.
All right, I'll give you guys a minute or so here to see if you can sketch what the derivative of this should look like. I'm going to restart the recording because I forgot to do it. I'm just going to quickly talk about this while you guys are working on that next one. Hopefully you already printed it off, but we started at a very small negative and went to a slightly larger negative because that's what our slopes were doing here. And since the function was decreasing, it was always negative. And then our function was always increasing, so it was positive from about 3 to fractional value, maybe a half. Then we had 3 linear pieces of slopes -1, 3, and 0. So we had 3 different sections with discontinuities in between. And I'll try to remember to restart the recording after you guys work on this one for a minute or two. All right, work on this one. All right, so let's again do the right-hand section first because it's easier. It's 2 linear pieces, right? So from 0 to 3, what's the slope?
Pretty low negative. Pretty high negative.
Well, we should be able to figure out exactly what it is. It's going down 2 and over 1, right?
Yeah.
Down 2 over 1,
It's
down 2 over 1.
-2.
So -2 from 0 to 3. And then immediately it jumps to a slope of 1 after that.
Yeah.
Okay, so that part should be pretty straightforward. But the first part of it here is more like a cubic, right? And we have a place where we have a local maximum. So what should our derivative be doing there?
Reach 0.
Should be 0. And then we have another place where we have a local minimum. So we should again have a place where our derivative is 0. And our function is increasing here, which means our derivative should be,
Very high. Start pretty high up.
well, if the function is increasing, though, what does that tell us specifically about the
Positive.
derivative? That the derivative is positive. And so if we think we have an endpoint here, so let's think, what is the slope at that endpoint about? Maybe
Around 4.
4 or 5, something like that. Okay, so let's see.
Yeah, a little bit of, starts a little bit above 4.
We'll just put it right there. I don't know, it doesn't have to be perfect. And then it's going to curve down here, and then we're going to, as soon as our function stops increasing and starts decreasing, we need to have a negative derivative. And right in the middle, it's going to change from being concave down to concave up. And so that should be right around here. We should have a local minimum. And what does it look like? The slope right there in the middle is -2, maybe?
2.
Yeah, okay. So we'll put a point there about -2. So we're just going to kind of curve down here and then curve back up. And then it ends up getting up to maybe about a slope of 1 there.
1.
Curves back up. And then we have an open circle there because we've got a linear on one side and a curve on the other. So. Does that look good to you guys?
Yeah.
I don't
So
know.
Matt-
I'm not sure if it would go from at one point from like -2 to -1. It goes up 2, but then after that, it just goes up 1.
From negative, you're talking about from -2 to -1?
Oh wait, actually,
I'm not sure what you're saying.
okay, never mind.
Okay, yeah. I mean, this right here is good enough. Like I was saying before, these don't have to be 100% perfect. They just need to be reasonably accurate. Anybody have any questions on that or no?
At x equals 0 is the whole at 1 because the slope of the original graph is about 1.
Yep, that's it. If you had it a little higher, a little lower, maybe not a little lower, but maybe a little higher than that, that'd be fine too. But,
Okay.
yeah. Cool. That's it. That's all we're going to do today. Now, let me stop this.